Hello and welcome. Today we're going to be discussing an important topic in chemistry, which is acid equilibrium. We're going to be calculating and solving for the equilibrium concentrations for acetic acid, which is a very common weak acid. First, let's start by understanding what happens when a weak acid like acetic acid is dissolved in water. Unlike strong acids, which dissociate completely, weak acids only partially ionize when dissolved in water, which means they establish an equilibrium between the undissociated acid as well as its ions. The extent of ionization is described by the acid dissociation constant, which we give the symbol K, which for acetic acid is around 1.75 times 10 to the minus 5 at 25 degrees Celsius. Now the magnitude of this value tells us that acetic acid ionizes only slightly, which is expected for a weak acid. For our problem, we're going to consider the equilibrium of acetic acid in water, which has the formula CH3COOH. Now this acid dissociates in water to form the acetate anion, or CH3COO-, as well as a proton, H+. Given that K sub C, our acid dissociation constant, is equal to 1.75 times 10 to the minus 5 at 25 degrees Celsius, and an initial concentration of acetic acid of 0.10 molar, what are the equilibrium concentrations for each of the species? We start with our equilibrium expression, where the acetic acid dissociates to form an acetate anion and a proton. Our equilibrium constant, Kc, is equal to 1.75 times 10 to the minus 5, and that's now equal to the product of our product concentrations divided by our reactant concentrations. Next, we need to set up our ICE table, which reflects the initial change in equilibrium concentrations. Our initial concentration for acetic acid is 0.10 molar, and our product concentrations are 0. The change then is reflected by negative X for our reactant and positive X for our products, leaving 0.10 minus X, and then X and X for the two products. We can then rewrite our equilibrium expression as X times X over 0.10 minus X, which is equal to X squared over 0.1 minus X. This implies that 1.75 times 10 to the minus 5 is equal to X squared over 0.10 minus X. We can simplify this to write 1.75 times 10 to the minus 5 times 0.1 minus X is equal to X squared. We can distribute the quantity to give 1.75 times 10 to the minus 6 minus 1.75 times 10 to the minus 5x equals X squared. We can then rewrite this as X squared plus 1.75 times 10 to the minus 5x minus 1.75 times 10 to the minus 6 is equal to 0. If we examine our expression closely, we see that it has the form ax squared plus bx plus c is equal to 0, which is a normal second-order polynomial where a is 1, b is 1.75 times 10 to the minus 5, and c is negative 1.75 times 10 to the minus 6. We can then solve for x using our quadratic formula, where x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2 times a. Substituting our values yields negative 1.75 times 10 to the minus 5 plus or minus the square root of 1.75 times 10 to the minus 5 squared minus 4 times 1 times negative 1.75 times 10 to the minus 6, divided by 2 times 1. Solving this expression is going to give two solutions, where we have positive 1.314 times 10 to the minus 3 or negative 1.332 times 10 to the minus 3. Now note that this is a real solution, so we want to have a positive value. This means that our first solution is going to be kept, and our second solution is discarded because it's not physically meaningful. Going back to our original expression for Kc, where we had x squared over 0.10 minus x, we can now write out the concentrations. So the concentration of acetic acid is 0.10 minus x, and is now 0.10 minus 1.31 times 10 to the minus 3, which gives 9.87 times 10 to the minus 2 molar. For the concentration of the acetate anion, it was simply equal to X, which is equal to 1.31 times 10 to the minus 3 molar, as well as our proton concentration equal to X, so 1.31 times 10 to the minus 3 molar. A common question that arises is, why was this process so mathematically involved? We can now examine our original equilibrium expression, where we had K sub C is equal to X squared over 0.1 minus X. If we look at the magnitude of X compared to the original concentration of acetic acid, we see that X divided by 0.1 times 100%, which is equal to 1.31 times 10 to the minus 3, divided by 0.1 times 100, is equal to 1.3%. This means that X is much less than the original concentration of acetic acid. So a logical question is, can we assume that X is equal to 0 in the denominator? If we rewrite our expression, assuming that X is equal to 0 in our denominator, we have that K sub C is approximately equal to X squared divided by 0.1. If we now solve for X, it is plus or minus the square root of 1.75 times 10 to the minus 6, which is equal to 1.323 times 10 to the minus 3. In examining the magnitude of this value compared to our original value of 1.31 times 10 to the minus 3, we see that we obtain nearly the same result, meaning that the approximation is valid. Let's take a moment to recap on a few things that we learned. First, we've introduced a general idea for solving the weak acid problem for a monoprotic weak acid, such as acetic acid. In our case, we saw that we can solve the concentrations at equilibrium using the quadratic formula, or if we approximate that the value X is small in the denominator, we can then calculate the concentration directly. Now, what we saw when we compared the magnitude of X to the original formal concentration of acetic acid, a value of 1.3% implies that the acetic acid is 1.3% ionized. Now, this approximation is generally only valid when the percent ionization is less than 10%. So one strategy is to do the approximation first, calculate the magnitude or the percent ionization, and then compare that to the original result. If the percent ionization is greater than 10%, then the approximation that we showed is not valid, and you have to go back and use the quadratic formula to calculate the equilibrium concentrations of each of the species.